black hole is one of the most mysterious and powerful things in the universe. It's a region in space where gravity is so strong that nothing, not even light, can escape from it. The idea sounds like science fiction, but black holes are real, and scientists have found many of them scattered throughout our galaxy and beyond. They are formed when very massive stars reach the end of their lives and collapse under their own gravity. When that happens, all of the star's matter gets squeezed into an incredibly small point called a singularity. Around this point is a boundary known as the event horizon. Once anything crosses this invisible line, it's trapped forever. It can't come back out or even send signals to the outside world. The concept of a black hole comes from Einstein's theory of general relativity, which describes how gravity works. According to this theory, massive objects, like stars and planets, bend space and time around them. The more massive something is, the more it warps space. A black hole bends space so much that it forms a bottomless pit. If you could somehow get close to one, you would feel an extreme pull that gets stronger the nearer you go. But you could never reach the center, because the laws of physics as we know them break down there. Time and space themselves seem to stop behaving normally inside a black hole. Even though black holes sound terrifying, they're not cosmic vacuum cleaners that suck up everything nearby. If our sun were suddenly replaced by a black hole of the same mass, the Earth would continue orbiting it just like before, though we'd be in darkness because there would be no sunlight. Black holes only pull in things that come too close. Farther away, their gravity acts just like that of any other massive object. The main difference is that a black hole's mass is packed into an extremely small volume, which makes its gravitational pull near the surface unimaginably strong. There are different kinds of black holes, depending on how massive they are. The smallest ones are called stellar black holes. They form when giant stars, at least 3 times heavier than the sun, run out of fuel and explode as supernovae. What's left behind after the explosion collapses into a black hole. These usually have masses between a few and a few dozen times that of the Sunday. Then there are intermediate black holes, which are larger but harder to find. They might form when several smaller black holes merge together, or when giant clouds of gas collapse directly. The largest kind are called supermassive black holes, and they sit at the centers of most galaxies, including our own Milky Way. The one in our galaxy is named Sagittarius A*, and it's about 4 million times more massive than the Sunday. Some supermassive black holes in distant galaxies are billions of times heavier than the Sun and power some of the brightest objects in the universe. Even though we can't see black holes directly, we can detect their presence through their effects. When a black hole pulls in nearby gas and dust, the material forms a swirling disk around it called an accretion disk. As the gas spirals inward, it gets extremely hot and glows brightly in X-rays and visible light. That's how scientists can spot where a black hole is hiding. In some cases, the material near the black hole shoots out in long, thin beams called jets, which can stretch thousands of light years into space. These jets move at nearly the speed of light and release huge amounts of energy. Astronomers can observe these jets with radio telescopes and use them to study how black holes interact with their surroundings. The first strong evidence for black holes came in the 1960 seconds, when astronomers discovered very bright X-ray sources in the sky. One of them, called Cygnus X1, turned out to be a star orbiting an invisible companion that was too massive and compact to be anything other than a black hole. Since then, scientists have found many more examples using telescopes that detect X-rays, visible light, and radio waves. In 2019, the Event Horizon Telescope project captured the first ever image of a black hole shadow located in the galaxy M87. The picture showed a glowing ring of hot gas around a dark center, which matched perfectly with what Einstein's equations predicted. It was a historic moment that turned black holes from theory into visual reality. Black holes challenge our understanding of physics because they combine two major theories that don't fully agree. General relativity, which explains gravity and large-scale structures, and quantum mechanics, which describes tiny particles and energy. At the center of a black hole, these two theories clash. General relativity predicts an infinitely dense point, but quantum theory suggests that something else must be happening. Scientists are still trying to figure out what really goes on inside a black hole. Some theories suggest that the singularity might not be a single point, but rather a strange, fuzzy region where space and time are mixed in ways we can't yet describe. Others propose that information that falls into a black hole isn't truly lost, but somehow stored or released later in subtle ways. If you could watch someone falling into a black hole, what you'd see would be bizarre. From your point of view, the person would seem to slow down as they got closer to the event horizon. The light from them would get redder and fainter until they appeared frozen at the edge, never quite crossing. But from their point of view, time would feel normal, and they would fall in quickly without noticing the moment they passed the horizon. This strange difference comes from how gravity affects time. Near a black hole, time slows down compared to the outside world. This effect, called time dilation, has been confirmed in smaller ways, near Earth and in orbiting satellites. But near a black hole, it becomes extreme. Some scientists think there might be miniature black holes that formed in the early universe, right after the Big Bang. These are called primordial black holes, and they could range in size from mountains to atoms. If they exist, they might make up part of the mysterious dark matter that fills the universe. However, none have been detected yet, and they remain purely theoretical. Still, the idea shows how black holes might not just be the remains of stars. They could also be relics from the birth of the cosmos itself. Black holes don't last forever. Over incredibly long timescales, they slowly lose mass through a process called Hawking radiation, named after the physicist Stephen Hawking. He discovered that, according to quantum theory, black holes can emit tiny amounts of radiation due to effects near the event horizon. This radiation causes the black hole to shrink very slowly. For big black holes, the process is extremely slow, much longer than the current age of the universe, but it means that even black holes eventually fade away. This was one of the most surprising and important discoveries in modern physics, showing that black holes are not completely black after all. The more we learn about black holes, the more questions we have. What happens to information that falls inside? Is there a way to connect black holes to other parts of the universe through something like a wormhole? Could black holes be portals to other dimensions or even new universes? These ideas are still just theories, but they keep scientists curious and inspired. What's certain is that black holes are not just destructive, they also shape galaxies, drive cosmic evolution, and maybe even hold clues to understanding the universe's deepest secrets. Black holes are often thought of as cosmic monsters, but in reality, they are also creators. They play a key role in shaping galaxies and helping stars form. At the centers of most large galaxies, including the Milky Way, lies a supermassive black hole that influences everything around it. These gigantic black holes act like engines, controlling how gas moves, how stars are born, and how energy flows through the galaxy. When gas and dust fall toward a black hole, the friction and heat can cause intense radiation that pushes other gas away. This process can slow down star formation for millions of years, creating a balance between growth and quiet periods. In this way, black holes regulate the life of galaxies instead of simply destroying them. Astronomers have observed galaxies where the activity around the central black hole is so powerful that it outshines all the stars combined. These galaxies are called quasars. A quasar is basically a supermassive black hole with a very bright accretion disk, swallowing matter at a high rate. The energy released is enormous, sometimes thousands of times brighter than an entire galaxy like the Milky Way. Quasars were first discovered as mysterious radio sources in the 1,950 seconds and 60 seconds, long before scientists knew what they were. Now we understand that they're among the most energetic and distant objects in the universe. And studying them helps us see how galaxies looked billions of years ago. Even though black holes can't be seen directly, scientists have developed clever ways to find them. One common method is to look for stars that seem to orbit an invisible companion. If the star moves quickly around something unseen, and if calculations show that the hidden object must be very massive and small, it's likely a black hole. This technique has revealed many stellar-mass black holes in our galaxy. Another way to detect them is by looking for X-rays from hot gas swirling around the black hole. When matter falls in, it heats up to millions of degrees and emits high-energy radiation that can be detected by space telescopes like Chandra and XMM Newton. In 2015, a new way to study black holes opened up when scientists detected gravitational waves for the first time. Gravitational waves are ripples in space-time caused by massive objects like black holes colliding. When two black holes merge, they send out waves that stretch and squeeze space itself. These waves were predicted by Einstein a century earlier, but no one had ever measured them until the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected one from two merging black holes about 1.3 billion light-years away. It was a major breakthrough that confirmed a key part of general relativity and gave astronomers a new tool to study the universe. Now, whenever LIGO and its partner observatories detect these waves, they reveal details about black holes that were once impossible to see. Gravitational waves have shown that black holes are more common and varied than we thought. Some of the mergers involved black holes that were dozens of times the mass of the Sun, larger than what scientists expected from normal stellar evolution. This has raised questions about how these black holes formed. Maybe some formed directly from the collapse of giant gas clouds, or maybe they grew by swallowing smaller black holes over time. Whatever the case, gravitational wave astronomy is helping us build a clearer picture of how black holes evolve and how often they collide. The study of black holes has also helped scientists explore one of the biggest puzzles in physics: what happens to information? According to quantum mechanics, information about the state of matter can never truly be lost. But when something falls into a black hole, it seems to disappear forever. This creates a paradox. If black holes evaporate over time through Hawking radiation, what happens to the information about the things that fell inside? Does it vanish, or is it somehow encoded in the radiation that escapes? This information paradox has led to intense debates and research for decades. Some theories suggest that the event horizon might store information like a hologram in a pattern of quantum ripples on its surface. Others propose that the information could be released when the black hole evaporates completely, but we don't yet know how that would work. To understand black holes better, scientists often use computer simulations. These models allow them to recreate what happens when matter falls in, how jets form, and how gravitational waves spread through space. The results have helped confirm many of Einstein's predictions with stunning accuracy. For example, time slows down near a black hole's edge, and the paths of light bend around it, creating strange effects. In fact, this bending of light, called gravitational lensing, can sometimes make distant stars appear brighter or duplicated in the sky. Astronomers can use this effect to detect objects that would otherwise be invisible, including black holes that don't have any gas or stars around them. One of the strangest things about black holes is how they blur the line between space and time. Inside the event horizon, the pull of gravity is so strong that time and space switch roles. Instead of moving forward in time, everything is pulled toward the singularity, as if it were moving through space. That means once something crosses the event horizon, it can't stop moving inward. It's as if all possible paths lead to the center. To an outside observer, though, the black hole just looks like a dark sphere that never changes. This difference between what's happening inside and what we can see from outside makes black holes some of the most mind-bending objects in nature. Over the years, scientists have also speculated that black holes might be connected to other regions of space through structures called wormholes. A wormhole is a theoretical tunnel that links two distant points in space-time. Some mathematical solutions to Einstein's equations suggest that a black hole could serve as one end of such a tunnel. However, real wormholes, if they exist, would probably collapse too quickly for anything to pass through. Still, the idea has inspired countless science fiction stories about traveling through black holes to reach other worlds, or even other universes. While these ideas remain unproven, they show how black holes stretch our imagination and push the limits of what we think is possible. Not all black holes are active. Many are quiet, meaning they don't have nearby gas or stars to feed on, so they don't produce light or radiation. These black holes drift silently through space, invisible except for their gravitational influence. If one passed through a region filled with gas, it could suddenly flare to life as the gas fell in and heated up. Some astronomers think that most black holes in the Milky Way are like this, dark and undetectable, unless something gives them away. There could be millions of these hidden black holes scattered throughout our galaxy, waiting to be discovered. Studying black holes doesn't just teach us about them, it also helps us test the laws of physics under the most extreme conditions. Every new discovery about them brings us closer to understanding how gravity and quantum mechanics fit together. In that sense, black holes are like laboratories in space, showing us how the universe behaves when pushed to its limits. They remind us that even the darkest, most mysterious parts of the cosmos can teach us something profound about the nature of reality itself. Black holes may seem like isolated monsters roaming the universe, but they are actually deeply connected to the cosmic environment around them. They help shape galaxies, influence star formation, and even regulate how matter and energy move through the universe. The relationship between a galaxy and its central black hole is surprisingly close. In many cases, the bigger the galaxy, the bigger its black hole. This pattern suggests that galaxies and black holes grow together, feeding each other over billions of years. When gas falls into a black hole, the energy released can blow away surrounding material, slowing down new star formation. But after the black hole quiets down, the leftover gas can cool and form stars again. This back and forth cycle keeps galaxies in balance. Our own Milky Way galaxy provides a perfect example. At its heart lies the supermassive black hole, Sagittarius A*, surrounded by millions of stars that orbit it like a swarm of bees. Scientists have observed these stars for decades, tracking their orbits to measure the black hole's mass. Some of them move at speeds over 5,000 miles per second, which proves how massive the object at the center must be. Despite its incredible mass, about 4 million times that of the Sun, Sagittarius A* is surprisingly calm compared to black holes in other galaxies. It's currently not feeding on much gas, so it's relatively quiet. But sometimes it flares up when a small cloud of gas or a star fragment gets too close and falls in, creating a brief but powerful burst of X-rays. The discovery of Sagittarius A* was a major step in understanding how galaxies work. It showed that supermassive black holes aren't just exotic features, they're an essential part of galaxy evolution. Astronomers now believe that nearly every large galaxy has one at its center. In some, the black hole is very active, consuming matter and shining brightly as a quasar. In others, like ours, it's more subdued. Over time, Galaxies can go through active and quiet phases, depending on how much gas is available for the black hole to feed on. This activity can have large-scale effects, even shaping the way galaxies look and how big they become. Even though black holes are extremely massive, they're also very compact. To imagine how dense they are, consider this. If the sun were squeezed into a black hole, it would be only about 3 kilometers wide, roughly the size of a small city. The gravitational pull near that tiny region would be so strong that light itself couldn't escape. The boundary around it, the event horizon, marks the point of no return. Anything that crosses it is gone forever from the outside world. Scientists often describe a black hole as having no hair, meaning it can be completely described by just 3 properties: mass, spin, and electric charge. Everything else about the matter that fell in its composition, structure, and details disappears behind the event horizon. Another fascinating feature of black holes is how they spin. Most of them rotate because the stars or gas clouds they formed from were already spinning. When that spin is conserved in the collapse, the resulting black hole can rotate at enormous speeds. Some spin so fast that their event horizons move close to the speed of light. This rotation affects the space around the black hole, dragging it along in a process called frame dragging. Near a fast-spinning black hole, space-time itself is twisted. If you were close enough, you would be forced to move around the black hole in the direction of its spin, even if you tried to stay still. This strange region outside the event horizon is called the ergosphere, and it's where some of the most energetic phenomena in the universe occur. The twisting of space there can even extract energy from the black hole, powering huge jets that shoot out into space. These jets are among the most spectacular sights in the cosmos. In some galaxies, they stretch for hundreds of thousands of light years, blasting out particles at nearly the speed of light. They come from material near the black hole that gets caught in magnetic fields and flung outward along its poles. Even though the black hole's gravity tries to pull everything in, the combination of spin and magnetic energy creates these giant beams that can light up entire regions of space. Jets can heat gas, trigger new star formation, and even limit how large galaxies grow. In this way, black holes can shape the fate of galaxies millions of light years away from them. For scientists, studying black holes isn't just about understanding how they work, it's also about using them to probe the laws of nature. Because they warp space and time so strongly, black holes allow us to test Einstein's theory of general relativity under extreme conditions. Every time astronomers observe a star orbiting close to a black hole or detect gravitational waves from a merger, they're effectively checking whether Einstein's equations still hold true. So far, the results have matched his predictions with incredible accuracy. But there's always a chance that future observations might reveal small differences, which could point the way toward a new theory that unites gravity with quantum mechanics. Another area of research focuses on what happens just outside the event horizon. Scientists have discovered that the space there is far from empty. It's filled with hot plasma, magnetic fields, and turbulent motion. These regions are difficult to study directly, but computer simulations and X-ray telescopes have helped us see them in new ways. The first image of a black hole's shadow, taken by the Event Horizon Telescope in 2019, revealed a glowing ring of hot gas surrounding a dark core. This was not an artist's illustration, it was real data, stitched together from observatories all around the world. In 2022, astronomers released another image, this time of Sagittarius A*, confirming that the same physics applies to the black hole in our own galaxy. These achievements proved that black holes are not just theoretical, they are visible, measurable parts of our universe. Even though black holes seem permanent, they actually have a life cycle. They're born when stars die, they grow by feeding on matter, and they can merge to form bigger ones. Over time, they can become dormant if they run out of nearby material to eat. But even in that quiet state, they continue to warp space around them and influence the motion of stars. At the end of the universe, when all stars have burned out and matter becomes rare, black holes may be the last objects remaining. They'll sit quietly in the darkness, slowly losing mass through Hawking radiation until they finally evaporate. That process will take an unimaginably long time, many trillions of years, but it shows that even black holes are not eternal. Because black holes involve such extreme physics, they inspire new ideas in cosmology and quantum theory. Some scientists think that what we call a black hole might actually be something more complex, like a fuzzball made of strings or a dense core that never truly collapses. Others have suggested that black holes could contain entire universes inside them, with new space-time regions that expand independently. These ideas sound wild, but they're based on real mathematical models that try to connect general relativity with quantum physics. If any of them turn out to be correct, black holes could be the key to understanding what happened at the beginning of our own universe. When we look at the stars and think about black holes, we are really looking at the extremes of existence. They are reminders that the universe is far stranger and more powerful than our everyday experience can show. Yet, in their mystery, they also reveal beauty, a harmony between destruction and creation, chaos and order. The same physics that makes a black hole deadly also makes it breathtakingly elegant. It bends light into rings, slows down time, and connects distant corners of the cosmos through invisible waves. Studying them is not just about science, it's also about wonder. Black holes don't exist alone in deep space. They're part of a much larger cosmic story. They form from stars, interact with galaxies, and leave behind clues that tell us how the universe changes over time. To understand them better, it helps to start with their origins. When a massive star, at least several times heavier than the Sun, runs out of nuclear fuel, it can no longer resist the pull of its own gravity. The outward pressure that once balanced the star's weight disappears, and the core collapses in an instant. The collapse releases a huge amount of energy in the form of a supernova explosion, one of the most powerful events in the universe. What remains after the explosion depends on the star's mass. If the core is very dense, but not too massive, it becomes a neutron star, a sphere of neutrons, only a few miles wide. But if the core is too massive, even neutrons can't resist the gravity. And the core keeps collapsing until it becomes a black hole. This process happens in just seconds, yet the result is permanent. The new black hole may be only a few miles across, but it contains more mass than our entire sundae. Any nearby material, gas, dust, or parts of the exploded star can start spiraling toward it, forming an accretion disk that glows brightly in X-rays. Over time, the black hole can grow by swallowing this material or by merging with other black holes. In some regions of space, especially near the centers of galaxies, this growth can be dramatic. A single supermassive black hole may have started as a smaller one billions of years ago, feeding slowly until it reached its enormous size. Scientists are still trying to understand exactly how supermassive black holes form. One theory suggests that they grow from smaller stellar black holes that merge repeatedly. Another theory says they might form directly from the collapse of huge gas clouds in the early universe, before stars even existed. Whatever the case, they seem to have appeared very early. Some quasars show supermassive black holes already existing less than 1 billion years after the Big Bang. That means they grew incredibly fast, faster than we once thought possible. How they did it remains one of the biggest puzzles in astrophysics. Even though we can't visit a black hole, scientists have come up with ways to study what happens near one using physics and mathematics. For example, when matter falls toward the event horizon, it speeds up and gets hotter, creating strong magnetic fields and shock waves. These effects can produce bursts of energy that we can detect with telescopes. The light from these regions carries information about the black hole's spin, mass, and how fast it's swallowing material. By studying these details, astronomers can map the behavior of black holes, almost like watching a wild animal in its natural environment. One of the most interesting aspects of black holes is how they affect time. Near a black hole, time moves slower because of the intense gravity. This isn't just theory, it's a real effect proven by experiments. Even near Earth, clocks in orbit tick slightly slower than those on the ground, and we have to correct for that difference in GPS satellites. Near a black hole, the effect is much stronger. If you spent 1 hour near the event horizon of a huge black hole and then returned to Earth, you might find that years had passed here, while only an hour passed for you. This extreme time dilation has become a popular theme in science fiction, but it's also a genuine consequence of Einstein's relativity. It shows how gravity doesn't just pull objects, it stretches and bends time itself. Another fascinating idea is what happens to light near a black hole. Light traveling close to it bends sharply, creating a ring-like illusion called an Einstein ring. When astronomers captured the first real image of a black hole, they saw this ring of light surrounding a dark center. The light you see in that image isn't coming from inside the black hole. It's from hot gas just outside the event horizon, glowing as it spirals inward. The black region in the middle is the shadow, where no light can escape. The image confirmed that the laws of physics hold true, even in the most extreme environments. It also gave people a powerful visual symbol of something once thought to be purely theoretical. While supermassive black holes dominate galaxies, smaller ones are scattered throughout the Milky Way. Some of them are part of binary systems orbiting a normal star. In these cases, the black hole pulls material from its companion, forming a bright X-ray source that astronomers can detect. Others wander alone, invisible unless they pass in front of background stars, where their gravity can briefly magnify the light through a process called gravitational microlensing. Using this method, scientists have begun to find isolated black holes drifting through space. They may not be rare at all. Some estimates suggest there could be as many as 100 million black holes in our galaxy alone. Even though black holes are deadly up close, they're not dangerous from far away. Their gravitational pull weakens with distance, just like any other objects. If our sun suddenly became a black hole with the same mass, Earth's orbit wouldn't change. We would keep circling it just as before, but of course, the planet would freeze without sunlight. That example helps show that black holes don't suck in everything indiscriminately. They simply follow the same rules of gravity as stars and planets, only much more intensely near their surfaces. Black holes have fascinated humans not only because of their science, but also because of what they represent, a place where the known laws of nature break down. They raise deep philosophical questions about the limits of knowledge and the nature of reality. What happens inside a black hole? Does time end there? Could something exist on the other side? We can't observe beyond the event horizon, so we can't know for sure. But some physicists think that inside, the laws of quantum mechanics might prevent a true singularity from forming. Instead, matter could be compressed to a very dense but finite state. Others propose that black holes might connect to white holes, which are hypothetical objects that release matter instead of absorbing it. If such a link exists, it could even form a kind of wormhole connecting distant parts of the universe. Though these ideas are speculative, they keep scientists thinking about how space and time really work. Black holes have become a bridge between theory and imagination, a testing ground for new ideas about quantum gravity, space-time, and the origin of the universe. They've inspired artists, filmmakers, and writers, turning into symbols of mystery and power. In many ways, they show how science and wonder often meet in the same place. The more we learn about black holes, the more they remind us that the universe is not just vast, but also deeply mysterious, full of surprises waiting to be uncovered. Even today, researchers are finding new ways to study them. Telescopes that can detect high-energy radiation, like gamma rays, reveal how matter behaves as it spirals into the abyss. Radio observatories like ALMA and the Event Horizon Telescope continue to refine images of black holes in nearby galaxies. Space missions like the European Space Agency's Gaia satellite help track the motion of stars, hinting at hidden black holes nearby. And gravitational wave detectors like LIGO and Virgo keep listening for the echoes of collisions billions of light years away. Each new observation adds another piece to the puzzle and brings us closer to understanding one of nature's greatest mysteries. In many ways, black holes are like laboratories that let scientists study the most extreme conditions in the universe. They combine enormous gravity, high energy, and the warping of space and time all in one place. That's why studying them helps us test the limits of physics. Einstein's theory of general relativity describes how gravity works. But it doesn't explain what happens on the tiniest scales, where quantum mechanics takes over. A black hole brings these two worlds together, the very large and the very small. At the center of a black hole, everything collapses into an incredibly tiny region called a singularity, where density becomes infinite and the known laws of physics break down. To truly understand this region, scientists need a new theory that merges gravity with quantum physics, a theory of quantum gravity. Many researchers believe that black holes may hold the key to discovering it. One of the biggest puzzles in modern science is called the black hole information paradox. According to quantum mechanics, information about the state of a system can never be completely lost. But when something falls into a black hole, it seems to disappear forever. If the black hole eventually evaporates through Hawking radiation, where does that information go? Stephen Hawking's discovery of black hole radiation in the 1970 seconds changed how we think about these objects. He showed that black holes are not completely black. They slowly emit energy due to quantum effects near the event horizon. This means they can lose mass and, over an unimaginable amount of time, eventually vanish. But if they disappear completely, what happens to the information about everything that fell in? This question has challenged physicists for decades and sparked new ideas about the fundamental nature of space and time. One possible solution is that the information isn't truly lost, but somehow encoded in the radiation that escapes. Another idea is that the surface of the event horizon might act like a hologram, storing information in a scrambled form. This led to the concept of the holographic principle, which suggests that all the information contained in a region of space could be represented on its boundary surface. In other words, our entire universe might work like a kind of cosmic hologram, where everything we see in 3 dimensions is encoded on a distant 2-dimensional surface. This idea sounds strange, but it has gained support from theoretical physics and has deep connections to string theory. If true, it could completely change our understanding of reality. Black holes have also become important in the study of gravitational waves. When 2 black holes orbit each other and finally merge, they send out ripples in space-time that travel across the universe. These waves were predicted by Einstein a century ago, but were only detected for the first time in 2015 by the LIGO Observatory. The discovery confirmed that black holes really do merge, and that their collisions release enormous energy, sometimes more than the combined light of all the stars in the observable universe during that brief moment. Gravitational waves carry information about the masses and spins of the merging black holes, allowing astronomers to study events that are invisible in normal light. Each new detection adds to our understanding of how black holes form, how often they collide, and how they shape the universe over time. These discoveries have turned black holes from abstract concepts into active parts of modern astronomy. Now, we can listen to the universe through gravitational waves, see black holes through their glowing accretion disks, and even map their effects through the motion of nearby stars. As technology improves, we'll be able to observe smaller and more distant black holes, perhaps even watching the moment one forms from a dying star. Future missions like the space-based gravitational wave detector, LISA laser interferometer space antenna, will be able to detect mergers involving supermassive black holes, opening a whole new window into cosmic history. The study of black holes also helps us understand galaxy evolution. When a supermassive black hole at the center of a galaxy becomes active, it can outshine the rest of the galaxy combined. The radiation and jets it produces can heat up surrounding gas, preventing new stars from forming. This feedback mechanism helps explain why some galaxies suddenly stop creating stars and why others grow slowly over time. Without the regulating influence of black holes, galaxies might have evolved very differently. In this way, black holes act as both destroyers and creators, destroying matter that gets too close, but also creating conditions that shape new structures in the cosmos. Even though we can't see a black hole directly, their effects are visible everywhere. For example, when two galaxies collide, their central black holes eventually spiral toward each other and merge. This process releases huge amounts of energy and may even kick the new, larger black hole out of the galaxy altogether. Some observations suggest that rogue, supermassive black holes might be drifting through intergalactic space, leftovers from these violent encounters. Studying these events helps scientists understand not only how galaxies grow, but also how the large-scale structure of the universe develops over billions of years. The connection between black holes and dark matter is another area of active research. Dark matter is a mysterious substance that makes up most of the universe's mass, but we can't see it directly. Some scientists think that black holes formed in the early universe, called primordial black holes, might make up part of this dark matter. These black holes could have formed just fractions of a second after the Big Bang, from dense regions of space collapsing under their own gravity. If they exist, they would be much smaller than ordinary black holes, perhaps the size of mountains or even smaller, yet still incredibly dense. Detecting them would help answer one of the biggest mysteries in cosmology. What is dark matter made of? Black holes also give us insight into the limits of what humans can understand. The physics near a singularity pushes our theories to their breaking point. We can write equations and run simulations, but beyond a certain point, the numbers stop making sense. This shows that our current understanding of nature is incomplete. Many scientists believe that once we fully understand black holes, we'll have a clearer picture of the entire universe, from its birth in the Big Bang to its ultimate fate. Some even think that the end of the universe could mirror the processes that happen inside black holes, with everything collapsing into a dense state before perhaps rebounding in another cosmic explosion. Even though black holes sound like the ultimate destroyers, they might actually be key to creation on the grandest scales. They recycle matter and energy, drive the growth of galaxies, and help shape the cosmic web that connects clusters of galaxies across billions of light years. Without them, the universe would look and behave very differently. They show us that even the darkest parts of the cosmos play a role in its balance and beauty. Black holes are among the most mysterious and extreme objects in existence. Yet, they are not just cosmic oddities. They are vital to understanding how the universe works on every scale, from the smallest particles to the largest galactic structures. The physics that governs them ties together ideas from relativity, quantum theory, and thermodynamics. Even though they seem like bottomless pits, black holes obey certain laws, much like any other physical system. In the 1,970 seconds, scientists such as Stephen Hawking and Jacob Bekenstein discovered that black holes have properties similar to temperature and entropy. Entropy is a measure of disorder, or the number of microscopic ways a system can be arranged. Bekenstein proposed that the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This idea was revolutionary. It suggested that all the information about what falls into a black hole could somehow be stored on its surface. Hawking later showed that black holes can emit radiation due to quantum effects, meaning they have a kind of temperature and can eventually evaporate. This discovery linked gravity, thermodynamics, and quantum mechanics in a way that had never been done before. It hinted that space and time themselves might be made of tiny, discrete pieces of information, like bits in a computer. In that sense, a black hole acts as a natural laboratory for testing the idea that the universe could be fundamentally digital. The study of black hole thermodynamics has since inspired many theories about quantum gravity and even the origin of the universe. The more we study these cosmic giants, the more we find that they may hold the key to the unified theory of everything that physicists have long sought. On a more observational level, astronomers continue to uncover new evidence of black holes in surprising places. For example, intermediate mass black holes, those between stellar and supermassive sizes, were once thought to be rare or even non-existent. But over the past few years, several candidates have been found in dense star clusters and dwarf galaxies. These objects could be the missing link that explains how supermassive black holes grew so quickly in the early universe. Finding and studying them is difficult because they are often faint and don't emit much radiation unless they are actively feeding. However, with next-generation telescopes like the James Webb Space Telescope and future X-ray observatories, scientists expect to discover many more of these in-between black holes, filling in a major gap in our cosmic understanding. Another fascinating discovery involves the behavior of matter just outside a black hole's event horizon. In recent years, astronomers have been able to watch hot gas orbiting extremely close to the event horizon of Sagittarius A*, the supermassive black hole at the center of our Milky Way. Using instruments like the gravity interferometer, they've tracked bright, hot spots of gas moving at nearly 1/3 the speed of light. These observations provide direct proof of Einstein's predictions about how gravity distorts light and time near such an object. When the hot spot passes behind the black hole, its light bends around it, briefly briefly creating a visible flare. The fact that we can now watch this process in real time is one of the most incredible achievements of modern astronomy. Meanwhile, black holes continue to surprise scientists with their diversity. Not all of them behave the same way. Some are quiet and barely noticeable, while others roar with energy. In some galaxies, the central black hole is so active that it produces powerful quasars, beacons of light, visible across billions of light years. These quasars were more common in the early universe, suggesting that black holes were much more active back then, feeding on large amounts of gas. Today, most supermassive black holes are calmer, but they can still wake up if new material falls toward them. This process can take millions of years, and we are only able to observe short snapshots in time. Black holes also influence their surroundings in surprising ways. Their gravity can compress nearby gas clouds, triggering new bursts of star formation. At the same time, the energy from their jets can heat gas and prevent it from collapsing, slowing star formation. This delicate balance shapes how galaxies evolve. Astronomers studying galaxy clusters have found that the amount of energy released by black holes at their centers is just enough to keep the surrounding gas from cooling too quickly. It's as if the universe has built-in feedback systems that keep everything in equilibrium. In that sense, black holes act as regulators, maintaining the cosmic balance between creation and destruction. In addition to their role in galaxies, black holes help shape the large-scale structure of the universe. When galaxies merge, their central black holes eventually sink toward the middle of the newly formed galaxy and merge as well. These mergers send out powerful gravitational waves that ripple through space-time. Over billions of years, this process has helped form the cosmic web, the vast network of galaxies and clusters we see today. Without black holes, the universe might be a far more chaotic and uneven place. Even though we think of black holes as regions of nothingness, they may contain the most concentrated form of information in existence. Some scientists propose that the interior of a black hole could hold a kind of quantum core that preserves everything that has ever fallen inside in some deeply encoded form. This idea ties into the concept of the holographic universe, where information and reality are two sides of the same coin. If this turns out to be true, black holes might not destroy information after all, they might transform it. This would solve one of the biggest paradoxes in science and reveal a hidden connection between physics and information theory. For the general public, black holes have also captured the imagination like few other scientific topics. They've become symbols of mystery, power, and the unknown. Movies like Interstellar have tried to depict them realistically, using real physics to show what they might look like up close. The film's black hole, Gargantua, was based on real equations from physicist Kip Thorne, who helped the visual effects team create the most accurate simulation of a spinning black hole ever made at that time. The results were so realistic that they even led to new scientific insights about how light bends around such objects. This crossover between science and art shows how black holes inspire not just curiosity, but creativity, blending imagination with discovery. And yet, for all that we've learned, the most profound mysteries remain unsolved. What truly happens inside a black hole? Does the singularity really exist, or is it replaced by some new kind of matter or structure? Could black holes be portals to other universes, or even seeds for new ones? These questions stretch the limits of our imagination and force us to confront the boundaries of human knowledge. Each new discovery brings us closer, but also reminds us that the universe is deeper and more complex than we can yet understand. Even so, the progress we've made in just the past few decades is astonishing. What was once a purely theoretical idea, an invisible point of infinite gravity, has become something we can now observe, measure, and even image. Black holes are no longer just mathematical curiosities. They are real, dynamic parts of the cosmos. And as we continue to study them, they may lead us to the next great revolution in science, one that unites all the forces of nature under a single, elegant theory.